Today we're going to look at composite functions. Sometimes they're called composition of functions. And basically a composite function is when you have two functions, you use one of them as an input. What I mean by that is generally we have a function, call it f of x. And then I'll give you a number, call it f of 2. And you evaluate the function at f of 2. Instead of having a function evaluated at just a number, such as the value of 2, we'll evaluate a function at another function or given another function. That means you'll have f of x and you have g of x. You could, for example, just for the term or the sake of writing out this notation, you could say f of g of x, meaning that g of x will now be your input. If we look at example set 1, we have two functions. We have f of x is equal to negative 4x plus 9, and we have g of x that's equal to 2x minus 7. Number 1 is telling us to evaluate the function at f of g of x. This stands for of. It's the same thing as saying f with an input of g of x. Okay, again, generally you would have a number right here, like the example above, I used the number of 2. But instead of inputting a number, this time we're going to input an entire function. We are going to input the function g of x, which is 2x minus 7. That tells us that we're evaluating the function f at 2x minus 7. If we're evaluating the function f at 2x minus 7, that means that we need to take a look at our original function f of x. Wherever we previously saw the value of x, we are going to replace that with the expression 2x minus 7. And you're going to simplify from there. If we're evaluating the function at 2x minus 7, tells us that we're going to rewrite this at f of 2x minus 7, which is equal to negative 4 times 2x minus 7 plus 9. So again, wherever I previously had x, I replace with 2x minus 7. And then you just simplify. Negative 4 times 2x, negative 4 times negative 7. That gives us negative 8x plus 28 plus 9. At this point, you simplify your common terms, giving you your final answer of negative 8x plus 37. For number 2, we're going to evaluate g of f of x. G of f of x is telling us to replace each occurrence in g of x with f of x. That's telling me that I have the function g. I'm replacing all x values with negative 4x plus 9. If I'm replacing all x values in g of x with negative 4x plus 9, I'm now going to have the function g of negative 4x plus 9 is equal to 2 times negative 4x plus 9 minus 7. And at this point, I simplify. 2 times negative 4x, 2 times positive 9. That's going to give me negative 8x plus 18 minus 7. Simplify your common terms. You have negative 8x plus 11. Your final answer is g of f of x that equals negative 8x plus 11. Next, we're going to evaluate composite functions. For these examples, we're going to use f of x that's equal to 2 times x squared minus 3, and g of x is equal to 4x. Number 1 is telling us to find f of g of 1. So I like to do these in a couple of steps. First, I'm going to evaluate g of 1 right here. That means I'm going to take this function and I'm going to evaluate it at the value or at the x value of 1. Once you find the g of 1 value, it will make it a little bit easier to substitute that into the f function. Now that we know g of 1 is equal to 4, I'm going to rewrite this as g of 4. That means I found the value of g of 1, it's equal to 4. Now I'm going to take this value of 4 and I'm going to substitute it back into my f function. All right, once I evaluate the f function at 4, I get my answer of 29. 29 is the answer to the entire problem. This is f of g of 1. And we know that after we simplified all of that work, we get the answer of 29. For number 2, we have g of f of 1. First, I need to evaluate the f function at the value of 1. F of 1 is equal to -1, which I can replace inside my composite function. And now I can evaluate the g function at -1. This would be 4 times -1, which is just equal to -4. That is the last step, telling us that g of f of 1 is equal to -4. All right, the domain of a composite function is the set of all numbers in the domain G such that g of x is in the domain of f. So that sounds a little bit confusing. If you read what I have typed out here, it says when finding the domain of a composite function, you must consider the domain of the inside function and the domain of the composite function. So you have multiple steps when finding the domain. All right, the steps for finding the domain start with finding the composite function. After you find the composite function, you need to determine the domain of the inside function. I used g of x to label this, but it's whatever function is on the inside or whatever your input is. And then you need to find the domain of the composite function. The domain of the composite function is the intersection of both domains found in step 2. And my helpful tip to you would be to sketch a number line and graph it from there. Or identify it from there, I should say. For the first function, we are finding the domain of f of g of x. For the first step, we need to find the composite function. The composite function is f of g of x. f of g of x indicates that g of x is the input or the inside function. That means we're going to be evaluating f at the g of x function, which is 4 over 3x minus 2. When we evaluate the f function at this value, we have 5 over, instead of writing x at this point, we're replacing x with our composite function. So we are going to have a new denominator of 4 over 3x minus 2 minus 1. Now we need to simplify this fraction, which means we need to simplify this denominator. In order to simplify the denominator, we're going to have to create a common denominator within that denominator. The common denominator is going to be 3x minus 2, and I know that because this is just a value of 1. So if we have a value of 1, we can multiply both the top and bottom by the same expression. And in this case, we're just going to multiply it by the common denominator expression. That's going to give us a new fraction of 5 over 4 divided by 3x minus 2 minus 3x minus 2 over 3x minus 2. At this point in the denominator, we can subtract, and when you're subtracting fractions, you're just going to subtract those numerators. We have a fraction of 5 over 4 minus 3x minus 2. This subtraction sign gets distributed to both terms, so we actually have 4 minus 3x plus 2, which is going to be negative 3x plus 6, all over 3x minus 2. Okay, if you lost me at that step, it would be 4 minus 3x minus negative 2, which is the same thing as adding 2. So when I combine my like terms of positive 2 and 4, I ended up with 3x plus 6. At this point, to simplify the fraction, we are going to multiply by the reciprocal. To do that, we have 5 over 1 as our numerator, and our denominator is going to now be multiplied instead of divided, and we're going to switch this second fraction, giving us 3x minus 2 as our new numerator, and negative 3x plus 6 as our denominator. We're going to multiply the numerators and the denominators together. Make sure you use that distributive property in the numerator, giving us the final simplified function of 15x minus 10 over negative 3x plus 6. This is your composite function, so this is f of g of x. Okay, that completes step 1 in the directions above. In the above directions, step 2 is to find the domains. And to find the domains, we need to find 2 of them. We need to find the domains of the inside function. In this example, the inside function is g of x. And then after we find the domain of g of x, we need to determine the domain of the composite function, or f of g of x. All right, starting with the domain of g of x. G of x is equal to the fraction of 4 over 3x minus 2. If you go back to simplifying or finding domains, you should remember that the denominator cannot equal 0. Therefore, I can set up an expression of 3x minus 2 cannot equal 0, giving me 3x cannot equal 2, or x cannot equal 2 over 3. This is one of our restrictions, so this is part of our domain. Finding the domain of f of g of x, which is 15x minus 10, divided by negative 3x plus 6. We have to do the same thing here. We have to find the domain, and by doing that, or to do that, we have to set the denominator equal to 0 and eliminate those values. Negative 3x plus 6 cannot equal 0, or negative 3x cannot equal negative 6. X cannot equal 2. Once we find the domain of both functions, the inside and the total function, step 3 is to combine both domains. So this is where I made the suggestion of a number line. The two domains include the values that x cannot equal 2/3 and x cannot equal 2. So on a quick number line, we know that x cannot equal 2/3, which is right here. We know that x cannot equal 2, which is right there. X can be anything in between. To write our domain for this function, we have all values of negative infinity to 2/3. We're excluding 2/3, so from 2/3 to 2, where we exclude 2, and then from 2 to positive infinity. For number 2, we have the expression f of g of x, where f of x is equal to 1 over x minus 2, and g of x is equal to the square root of x plus 4. Following the same order as above, step 1 is to find the composite function, f of g of x. All right, when we're inputting the function, the square root of x plus 4, we're left with a fraction of 1 over the square root of x plus 4 minus 2. We cannot simplify anything here. This is our composite function. So in step 1, f of g of x is equal to 1 over the square root of x plus 4 minus 2. Step 2 is to find the domains. The first domain is going to be of g of x, which is your inside function. G of x is equal to the square root of x plus 4. And if you recall from previously, if you have a square root, whatever is under that square root sign cannot be a negative. We have to set an expression of x plus 4 greater than or equal to 0, x has to be greater than or equal to negative 4. Next, we find the domain of the composite function. The domain of the composite function is found using f of g of x, which is 1 over the square root of x plus 4 minus 2. We have two things going on here. We know that the denominator cannot equal 0, and also that x plus 4 cannot be a negative. But we don't really have to worry too much about that because we already did x plus 4 cannot be a negative in step 1. So all I'm going to take care of here is that the denominator cannot equal 0. Therefore, I set up an expression. The square root of x plus 4 minus 2 cannot equal 0. The square root of x plus 4 cannot equal 2. Square both sides. X plus 4 cannot equal 4, or x cannot equal 0. All right, last step. Step 3 is to combine the two domains. So the two domains tell us that x has to be greater than or equal to negative 4, but also that x cannot equal 0. Sketch a number line. We know that x has to be greater than or equal to negative 4, so that would be a solid point at negative 4, but that it cannot equal 0. So it's anything between negative 4 and 0, omit the value 0, and then anything to positive infinity. The domain would be a square bracket from negative 4 to 0 with a round bracket, and a union 0 to positive infinity. In the last part of the notes, we have to decompose a composite function, meaning we have to break apart the composite function and find what it could have originally been. So the directions are saying that h of x is equal to f of g of x. That means that in the first function where we have h of x, and we know that it's equal to 1 over x plus 1, we also know that 1 over x plus 1 is equivalent to f of g of x. So we need to break this apart. We need to think, all right, if f of g of x is equal to 1 over x plus 1, what could the original function be? So what is it that you start with, and what could the input be? Make this easier for yourself. Like, think of just a simple variable expression and then have the input be something that's a little bit more complex. So for example, in this function, I'm going to tell you that f of x could just be something as simple as 1 over x, and then g of x be x plus 1. That means when you substitute g of x into the function, so when you substitute x plus 1 into the function, you're substituting it in for x, and you're replacing that denominator. This right here could be the potential decomposition of functions. Now there can be more than one answer, but I would advise you to always go with the simplest answer you can think of. For number 2, we know that h of x is equal to f of g of x. Approach this the same way we did number 1. Think to yourself, what could the outside function be? And we're looking for something simple. And what would the inside function be? So I would break this apart. The outside function be something as simple as the square root of x. The inside function be the expression, so the more complex part. Make the inside function be x squared plus 1. That tells you that when you substitute g of x in for f of x, you're replacing your x value with x squared plus 1, which will give you your original expression.